In the last video, we looked into encryption and learned how to turn ordinary text into a visual grid. Remember, it looks just like a pattern of squares, but it's actually hiding a secret message. We used a strong encryption method, the AES 256 CBC, to scramble our data and then represent that scrambled data visually using black and gray squares. But an encrypted message is only useful if you, the intended recipient, can unlock it. So in this video, we're going to dive into the decryption process and see how to reveal the secret message hidden within this image. And the secret key, as always, is the password we used for encryption. The first step in decryption is to reverse the visual encoding. We need to read this image and convert it back into a binary sequence, which is a series of ones and zeros. Remember, in our encoding, a black square represented a 1 bit, a gray square was a 0 bit, and any white squares were just padding. We start by carefully examining the image square by square and translating the colors back into their binary equivalents. This gives us a long string of ones and zeros, which is the step back to our original message. To accurately read the grid, the system first needs to figure out the size of each individual square. We want this process to be automatic, not requiring manual guessing. And to do this, it scans the image, hunting for where the colors shift black for a 1, gray for a 0, and white as padding. It measures the consistent gaps between these changes to lock in the exact size of each square. Once it's got that, it moves square by square, translating the colors into a long string of ones and zeros, which is the binary sequence we need. Remember, the white squares were just filler to make the grid square, so they are ignored during this conversion process. They don't represent actual data bits. Once we have our bit sequence, the next step is to group these bits back into bytes. We take our long string of ones and zeros and divide it into chunks of 8 bits, where each chunk of 8 bits represents a single byte of encrypted data. Now, for the core of the decryption, we're still using the AES 256 CBC to unscramble our data. This is where our secret key, which is the password, and the initialization vector, or the IV, come into play. Let's walk through how it works. First, we take the password and run it through a hashing function, the SHA-256, as before, and this transforms the password into a precise 256-bit key that the AES needs to unlock the data. Next, we grab our byte data. The first 16 bytes are the IV, which we separate out, and the IV was mixed into the encryption process to scramble things uniquely, and we will need it to start the decryption right. The rest of the bytes are the ciphertext, or the scrambled version of our message. Now, we launch the AES 256 CBC algorithm in decryption mode. During encryption, we added something called PKCS 7 padding. That padding is still there, tacked onto the end of our decrypted data. To strip it off, we look at the last byte of the decrypted output and we chop them off. This leaves us with the exact original data. Finally, the last step is to convert our decrypted binary data back into human readable text using UTF-8 encoding. And this is the same encoding we used to convert text to binary in the encryption video. And there it is, the original message revealed from our visually encrypted grid. By reversing each step of the encryption process with the correct key, we've successfully decrypted our secret message. So, that's how decryption works for our visual encryption method. I hope you found this video interesting and educational. You can explore the full code on my GitHub repository. The link is in the description below. Feel free to download the program, try it out by yourself, and even experiment with how it works. Thank you so much for watching, and if you enjoyed this video, please like and subscribe for more other fun tech projects. See you in the next video. Cheers!